Did anybody get all 2s, 4s, and 5s, or a lot of 2s, 4s, and 5s in their rolls? And I'll let you define what a lot is. Anybody get a lot of 2s? Anybody get a lot of 4s? Anybody get a lot of 5s? I'm curious.
And I got a bunch of 1s.
And a bunch of 1s, which is like Jenny. So good. There we go. Okay, good, good. Did anybody get the same number of 1s, 2s, 3s, 4s, 5s, and 6s? Good. Very, very good. Good. We have to accept what? Lots of? Exactly. Large margin of error. Good. Very good, friends. Thinking like statisticians. Makes me happy. Thinking like statisticians. Not thinking like mathematicians anymore. This is good. This is good. I told you you would. I told you I didn't infect you yet. All right. Now, what we're going to do is we're going to set up a distribution of our results. Distribution of our results. X and F, just like we've always done. L1, L2. X is the number of pips. Pips is a funny little word. I think it's English, yeah. And it's the number of dots on a side. So what are the values that the pips can have? 1 through 6 on a single die. You got a 1, 2, 3, 4, 5, 6. Excellent. Excellent. What I want to do next is we're going to collect our data as a class. So I'm going to go around the room. I'm going to shout out the number of pips. Raise your hand, and on your hand indicate how many of that time you got. Does that make sense? So how many of you got 1s? Raise your hand and then show me how many 1s you got, and I'll be able to count them up and put them in the F column. So we got, this is 1s now. 4, 6. Well, you know, I used to use clickers, but getting the clickers plus the camera plus the Excel is just a pain in my ass. So this is much easier this way. Sorry, I lost count. 4, that's proving your point, Harrison. 4, 6, 7, 8, 10, 15, 16, 19, 22, 26, 29, 31, 35, 44. All right. 44 1s.
You mean 2s?
I meant 1s.
Oh, I thought you were going to the next one. I'm just like...
You just threw off the whole data set now.
I'm going to 2s now. 2s, how many 2s we got? No, how many 2s we got? How many 2s we got? We got 1, 4, 5, 10, 14, 17, 19, 26, plus 5 is 31.
That's good job.
Excellent. Excellent. 3s. How many 3s do we have? 3s. We got 6. That's quite all right. 6, 10, 14, 19, 24, 26, 30, 35, 40, 44, 46. Excellent. Excellent. 1, 3s, and 6s, right? 4s. Let's get some 4s up here. Let's get some 4s up here. We'll also see how good I can count at the end of this. 3, 4, not very good. 4, 9, 11, 13, 15, 16, 18, 21, 23, 24, 26, 33, 34, 35, 36. Okay. 5s. 5s. That was good. That was good. What was it for? Just out of curiosity. Oh, it's usually. Just out of curiosity. What are you noticing?
It's kind of making a pattern.
Oh, that's interesting. Let's go back to that. Oh, 5s. We got 5s. We got 4, 5, 6, 8, 10, 13, 16, 18, 20, 22, 24, 26, 27, 28, 29, 30. Damn, pattern's going. And I was hopeful. I was hopeful it wouldn't get to you because I want to have to explain a pattern that shouldn't be there. So there shouldn't be a pattern like that. There should be a pattern, but we're just not seeing it here. 6s. 6s. Now, if I was clever, I could do some mathematics and do this, but by the time I do it, I'll screw it up and it's easier just to count. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. I think I got you, Michael. We had a 1. I think I got you. All right, if I added correctly, which I didn't, I can tell by looking at it already, that would sum to a multiple of 10. It doesn't. 12, 13, something, 20, 17. Yeah, 17. 5, 8, 12, 15, 18, 217. Do we have 22 of us in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 4.
So Jackson and I,
I'll show you.
we came in halfway and we didn't roll dice.
Oh, you didn't roll dice! So it should be 220, not 240. And now so I'm only off by 3. I can live with that. I cannot live by being off by 23. I can live by being off by 3. Get some dice. Well, I guess we'll get the dice in a
We
minute.
didn't know how many times we were
That's
rolling when
all-
we came in, so we were just like,
We'll get you.
okay.
So anyway, there's my sum of frequencies. Now,
Those are bubbles.
my question is, are there any unusual rolls? Any unusual rolls there? Now these are the rolls, 1, 2, 3, 4, 5, and 6. Any of them unusual? Any outliers?
Isn't the 46 in that letter?
I don't know. How are you quantifying it?
I gotta graph this real quick.
Harrison, say it a little bit louder, please.
This is my calculator.
I gotta graph this real quick to take a look. Yeah, I think we should, yeah? Yeah, I think we should. It's impossible to know whether something's an outlier. And Megan, I love what you said. Because what you said is, I went to the big one, and the big one looks too big. But too big is so relative. We have to know what too big actually means. Let's take a look at too big. All right, stat, let's turn it on first, that might be helpful. Stat, edit, let's clear out all this stuff. Clear. Okay, 1, 2, 3, 4, 5, 6. Got our data points, or our frequencies. Don't need L3 either, we need to get rid of him. Whoops. Oh. There we go. Make sure you, when you hit your plots, make sure you change your lists. Because now our data is, well, at least my data is in L1 and L2, and if you try to graph L4, it might get confused.
I don't know. I'll have one of those things.
Okay, L1, L2. We'll zoom stat. Not bad. I'm going to finagle, as Megan says, because I do. 1 to 7. This seems a little weird to go 1 to 7, maybe. It seems a little weird for me to say I'm going to go 1 to 7. Hopefully that feels weird to you. The reason it should feel weird is that it always graphs continuously. So when I type 1 with an x scale of 1, let's see if that works. Nope, maybe the y max taller too. We'll go up to, what was your highest? Your highest was 46. I can go up to 60. That should do it. Make this 0 maybe. I'm just doing some Math 95 stuff now real quick. I want to re-explain this better up here. So, that wasn't high enough. So, 7 by 7.
There needs to be L1.
There. So the reason why it goes 1 to 7 is this bar, which is the number of times we saw 1, actually spans 1 to 2 on the axis. This bar, 2 to 3. This bar, 3 to 4, 4 to 5, 5 to 6, and 6 to 7. So that bar is the 6th bar, but it starts at 6 and goes to 7. Is that fair? That's why your box plot doesn't go past that, because that's 6. That right there is 6. The way to get around that, I guess, would be to somehow shift your data by a half. You have to subtract a half from each of your data and drop it down, but that gets too finagly. It's easier just to kind of make peace with the fact that we have to make that adjustment on the x max. Is that fair? It gets too Math 111-y otherwise, and I hate mentioning that class in there because it makes everybody kind
So
of
how
dry.
did you get them all squished together?
Oh, so check it out. Thank you. Great question, Jen. I said if I want to make it look like a histogram with 6 bars, I need to make it 6 wide. It was, I think, 8 wide, which is why it had gaps between it. And the scaling was 0.555, which is a very strange scaling. So I set the scale to 1.
Okay.
And that means each of the bars is going to start at 1, go 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and then 6 to 7. That's why I had to set that at 7. If you go to 8, you're going to notice that there'll be a bar missing. So it's annoying. Because in Excel, what you do is you right-click on the graph and you put gap width 0. You slide a slider down and it connects. It's 1986. Cool? All right. Any outliers, friends? Any outliers? Doesn't appear to be. Any of them? Let's check all the measures. Number 1, would you use standard deviations? I definitely would not, because the data is not bell-shaped. We've got no tails. We've got a lot of but no tails. Do you think if we kept doing this experiment, we'd get tails? Remember how I said sometimes you have to do an experiment a long time until you get the shape to show up. Do you think you'd actually get tails? If you got tails, what would that imply about the rolls?
But they're not equally likely to get that.
Yeah, if we got tails, that would mean we'd see fewer and fewer 6s and 1s. But the pattern that we're seeing right now is that that's not the pattern that initially showed. So either we saw a bunch of 6s and 1s that we shouldn't have seen off the bat, or we saw exactly what we should have seen off the bat. We'll come back to that. Thank you, Scott. Good. So we can't use bell curve. Can we use IQR? I don't see why not. It's a distribution that looks just fine. I think by IQR it's fine too. And there's your IQR, 50%. Everything's well within that. Can we use the 5% cutoff rule? Well, I don't know. Let's get the percentages, shall we? Let's get the percentages. And I'm going to add another column over here, if it's okay with you guys, for those percentages. So I'm going to put, your book calls it relative gravity. Your book calls it relative frequency. I got to hold these different. Relative frequency. Relative frequency is just a fancy name for percentage, proportion, probability. It all means the same thing. It's just a percentage. So those percentages that you guys are doing in your projects, they're all relative frequencies. How often do they occur when compared to 100% of the whole? So what we have to do, and I'm going to show you how to use your TIs to be a spreadsheet again, if it's okay with you guys. You have to divide each of these numbers by that 217. Now one way to do it is actually to do each one, but let's not do that. Let's go back to our data. Stat edit. But before you do that, commit that to memory right now. Okay, just let that burn into your memory, what that looks like. Okay. You know what? Let's be fancy. Let's be fancy. Let's take a picture of it. I knew, yes. There we go. And we will save that on the desktop as captured. Okay, I don't have to remember it anymore. Okay. Stat edit. Let's go to L3. Go up on top of L3 and type this command with me. Make sure you're on top of L3 like I am up there. Type second 2 divide by 217. And when you press enter, it'll spit the proportions out for you, right there. Let's put those in. What's that, 20% for L3? 14? 21, yeah? Oh, good, if you guys don't mind. 21?
17.
17?
14.
14 and 14? Beautiful. Let's check for rounding error real quick. The sum of those relative frequencies. Does it sum to 100%? It might not sum to exactly 100 depending on rounding. Zero, that's a 0 there. So 5, 12, that looks as a good sign so far. 0 carries a 2. 4, 5, 6, 7, 8, 9, 10, hot damn! 100. Now we know it theoretically has to sum to 100% because we're adding 6 fractions together that add up to 217 over 217, but it's possible always to introduce rounding error when you truncate. On average, it balances. That's why we round the way we do. You ever thought about that? Why we do the rounding that we do? I should swing this over here so we can see it. Did you ever think about why we round the way we do? Why the rounding rules are set up the way they are? If it's 0 through 4, keep it the same. If it's 5 through 9, round up. Do you ever think about why you do that? Probably not. Somebody told you to do it. It's the halfway point of assumed uniform distributed data. So the lower half, you leave it as it is. The upper half, you round up. I got into a discussion one day with a guy who said, yeah, that rounding rule's biased. I'm like, what do you mean? He's like, because you're rounding up for half of it. I'm like, yes, and you're rounding down for the other half. And he said, yes, but you're going to inadvertently inflate your estimates. I'm like, you're assuming there are more numbers from 5 to 9 than there are from 4 to 0. He's like, exactly. I'm like, have you looked at a number line? It's exactly the same number of numbers 0 to 4 that there are from 5 to 9. And we had this wonderful discussion, and it was great. We made a lot of potato chips that night, I remember correctly. But it was interesting, that misconception of what the number line actually looks like. Anyway, beautiful. Relative frequency sum to 100%. Now, everybody, if you would, take a look at that graph. So graph L1 and L3. Now, graph L1 and L3 versus L1 and L2, and let me know what you notice.
So we turn plot 2 off.
You can leave them on and just change the L2s to L3s. That works. So all I'm doing, I'm leaving the same plots on, but I'm changing the frequency lists to L3 instead of L2. That way you can kind of keep everything in the same place, if that makes sense. Does that make sense? I'm just changing the frequencies to the relative frequencies. On both plots, yeah, for sure. So everything, I'm trying to create less work for y'all. So just change L2s to L3. So friends, if you're looking at it from what we're doing here, what we just looked at before, this was our distribution. Now we're looking at this as our distribution. That's all. That's all. Is that fair? Is that believable? I don't sense confidence on average. We okay? Take a look. Take a look. Take a look. Let's go back to here. Now, if you just press graph, it's going to be a little bit misleading because you're not going to see a histogram. And there's a very simple reason for that. You know what the very simple reason is? It's there. It's there. JC's like, no, it's not. I don't see it. If you press trace, it's definitely there. It's just really, really low because your window's set. Yeah, thank you, because your window's set to frequencies. If you press zoom stat again, zoom 9, now you're going to have to play with it. You're going to have to play with it. You're going to have to play with it. So we're going to have to go from 1 to 7 by 1s. And now you have to adjust this guy right here. You have to adjust this guy to your new frequencies. Now remember, your new frequencies are decimals. They're percentages between 0 and 1. So you might want to pick a number like, I don't know, like 0.6 or something like that. That might leave room for the box plot. Oops, 0.1. There we go. There it is. And you can play. If you want the bars to be taller, you can play. You can play with the scales a little bit. Did you ever see the window I used? Does this look familiar up here?
Yeah.
171, same one I used for the other one. I don't know why, FYI, I don't know why. When you try to graph these relative frequency distributions, I cannot explain to you why the TI immediately puts 2 bars on there. It does it every time. As soon as you go to percentages, it puts 2 big fat bars, and I do not know why it does that. This is why I spend so much time finagling, because I want you guys to feel comfortable, like, oh, I don't like that graph, I'm going to change it to something else. Fair? Good, good. I'm going to change this Y max to a little bit lower, I think. Maybe 0.5. Let's see what that looks like. That's not bad. That's not bad. We can mess with it some more. Does that look familiar? Does that look familiar, friends? Yeah, let's take a look at this. There. Take a look. Now hang on!
No, scoot them down. Can you scoot them down?
Yes, I can. I'm sorry. Maybe just this real quick. Oh, I see what you're saying. I should have said no. I'm not a bastard, usually. Now, I know it doesn't look exactly the same. That's because I have to set the window exactly the same. I'm trying to finagle with it so I get it close. Let's see how that looks. Oh, that looks pretty good, doesn't it? What do you notice, friends? It's the same shape, isn't it? It is most definitely not the same graph, because one is frequencies and one is relative frequencies. But it is the same shape. In other words, this one is as many times taller than this one as this one is to that one. Hopefully that makes sense. There's definitely a correlation there. Fantastic. Now take a look at this. Look at the box plots. Any difference in the box plots? Absolutely none. As a matter of fact, the box plots are easier to perceive in this one because you actually have the percentiles. If you did some sums of these percentages, you'd actually get the percentiles, which we were just talking about a week ago. Yeah, good stuff, good stuff. Now, the question I have, or I guess the statement, I want to stop momentarily, and I want to get back into to Jenny's data because it's fantastic, the 6s and 3s and the 1s. But I want to talk real quickly about what you guys just constructed. In this, use some different colors here. Let's use green. When you guys created this distribution right here, with that as your L1 and this as your L2, you created what's commonly called a probability distribution. Now, up till now, your book has been calling it a relative frequency distribution, and that's fine. I kind of like the fact that it was calling it a relative frequency distribution because I wanted to build the idea of probability through the projects. So I wasn't opposed to you calling it relative frequency because that's something we can understand coming into a prob class without ever talking about probability before. But probability is where I want to go now. So I'm going to come over here and I'm going to set up a term. Probability distributions. This is where pretty much the rest of the course is going to be living. Pretty much everything we talk about from here on out is going to be about these guys. This is why you guys pay what you pay for your car insurance. This is why you guys pay what you pay for your cell phone bill. This is why you guys pay what you pay for your gas bill. This is why you guys pay what you pay for health insurance and life insurance and every other kind of insurance known to man and woman on earth. It's all based off of these things. Next class I'll have a little in-class quiz where you actually analyze my chance of death and or dismemberment based on the state of Oregon and the CDC. Cool. Well, we're going to analyze it using one of these things. But before we get to that, let's break down what they actually are. And what they are, there are two kinds of them. There are discrete ones, and there are continuous ones. With your permission, I'd like to hold off on these for now. No. Megan says no. I'm going to override Megan's vote and hold off on them for now and focus only on the discrete ones. Okay, thank you. Just because I'm looking out for your best interest. We're going to focus on the discrete type now. And the reason I like the discrete type is there is a finite number of elements in the left column. So you've got a left column and a right column. You can express these things a number of different ways. You can express these things as tables, and we're going to spend a lot of time using tables today and also Thursday. You can express them as tables, you can express them as graphs. I like that too. We'll look at one of those today, one of my favorite types of graphs. And you can also express them as equations. Of these three methods, we're going to focus on these two the most, and of those two, we're going to focus on this the most, because it's the most easily computable. I take that back. This is actually the most easily computable, but nobody seems to like them except math people. So we're going to stick away from these for the most part and stick mostly with tables and graphs. Okay? Because I think they're more concrete. You can see a table, you can see the results of an experiment. If I tell you P of X equals 1/6, everybody kind of goes, what? That sounds like Math 111, and then just draw leaves. So we're going to leave the equations go for the most part. I do want to refer to them every once in a while, but tables and graphs are nice. Now, of the tables, I'm going to mute the screen for a second. Of the tables, you'll notice you've got two columns. You've got the X column. I'm going to call that the X column. That's the left column. I mean, usually, it makes the most sense to have it be the left column. It's the most logical. What is in there? What is in that column? What was in it for us? Good! And how did you know it was 1 through 6? Because when you look at your die, you realize that I can either get a 1, or a 2, or a 3, or a 4, or a 5, or 6. Nobody bothered putting a 0 in there, or a 13 in there, or 22.2 in there, because you can't get that. So you know that it's either a 1, a 2, a 3, or 4, or 5, or 6. So then you grab the die and you go to roll it. Do you know what you're going to get?
1 through 6.
Good, good. You don't know what you're going to get, but you know it's going to be between 1 and 6 inclusive. Nice, nice. And that's exactly what is described in the left column. It contains what are called random variable values. This is a great word. I love this word, or a great phrase. You know it's going to contain 1 through 6 inclusive and discretely. 1 or 2 or 3 or 4 or 5 or 6. You don't know which one you're going to get each time, but you know you're going to get exactly one of them. And that's the definition of a random variable. A random variable is somehow dependent on chance. I say somehow because of the way Jenny answered my question. You don't know what you're going to get, so there's the somehow part, but you know you're going to get from 1 to 6. So you know the outcome, it's just not sure which one you're going to get. Just like with Gallup. When Gallup wants to survey 1,000 Americans and ask them yes or no, is Congress doing a good job? Yes or no? They don't know what's going to happen after they ask 1,000 people, but they do know what one of the results could be. One of the results could be half of them say yes, half of them say no. Not likely in this political climate. More likely, 2 of them say yes, 998 of them say no. You see what I'm getting at? So they don't know which one they're going to get, but they do know they're going to get something in a table that has 1,001 values on it. More on that in a little bit. So that's the X column. The right column, which up till now we've been calling the relative frequency column. Relative frequency column. We're going to start calling that the probability column, or the P of X column. Just because I want to start getting you guys to think in terms of probabilities and the interchangeability with percentages. And I like the shorthand, the P that you guys learned in your first project of probability of. And then X, although this looks like Math 111, it's not. All that X is whatever the value is in the previous column. And we'll talk more about that. I'm going to add an alternate column to this in a second. So all it contains is the probabilities of each random variable value. The probabilities of each random variable. That's all it contains. Now what I want to do, that's kind of a real quick breakdown of what a probability distribution is. I hate getting all lectury, but every once in a while it's like these are just terms we have to kind of make peace with. So there's some terms to make peace with. What I want to do is I want to swing back over to this. And if it's okay with you guys, I'm going to put relative frequency percent. This is technically a probability column. It's the we saw with probability of 20%. 1 in 5 of us, or 1 in 5 of our rolls were 1s. 14 out of 100 were 2s, and so forth and so on. Right? Those are all the results from our experiment. I'm going to call this empirical. I'm not going to put it in black. I'm going to put it in a different color so it stands out.
You can get theoretically.
Say that again!
Oh,
Say that again! No! Go! I heard theoretical! Say that!
I was saying theoretically the relative frequency should be like the percent that each roll is going to happen.
Yes! That's what I was going to compare and contrast with, Harrison. Thank you!
So it's
You read my mind!
sweet.
So what Harrison has just pointed out to us correctly, I might add, is that we can apply what we know about dice. Now, we can apply what we know about dice. What we can't do is apply this to anything else except a single die. But right now, that's all we're at, is a single die. We could have created this column without actually having you guys roll dice at all. I'm going to call it the P of X column. And I love the fact that you call it theoretical, Harrison. We're going to call this theoretical. Not empirical. Empirical implies that we did an experiment and collected data and then reported back on the data. I'm going to do theoretical, which means I'm going to assume something about these dice. And what am I going to assume about these dice?
But they're not weighted or anything.
They're going to land on any face with equal likelihood.
The chance of each one is equal.
Exactly. And what would that chance therefore be?
Probability.
1 in 6. The probability. Say that again. Careful. I mean, it had 5 sides. More like 17%. 16.666% to quote Scott's. One hand from earlier. But yeah, about 1 in 6 would be the theoretical. So now, just so you know, so you're not afraid of this notation, you would therefore say the probability of 1 pip would be 1 in 6. The probability. Oh, good lord. These are shorter than the last ones I used to use. I used to hold them like this. Probability of 2 pips would be 1 in 6, and so forth. Probability of 3 pips, 1 in 6, and it's all going to be 1 in 6. Because what are you assuming about each face of the die?
Equal probability.
Equal probability. That's kind of the point of a die, of a die or a pair of dice, is that each face is equally likely. So you're not cooking them or weighting them. So a 6 is just as likely as a 1. That's why Jenny was so interested in her results of 6, 3s, and 1s. Like, wait a minute, if they're equally likely, we should be seeing just as many 6s as 3s, as 4s, as 1s, as 2s, as 5s. Did we see that? Hold that thought. Hold the answer to that question. It's a loaded question. The question is, did we see these? Now these are all about 16.7%. I see no 16.7%. That's close. That's close. Are these arguably different than 16.7%? Hold that thought. It's a loaded question. What I want to attack now is, well, first of all, if I was to add all these up, if I was to sum up all the probabilities of x, just like the percentages sum to 1, so do the probabilities. Now this is a function of mathematics, but it's also a function, hopefully you see, of logic. They have to add up to 1. If you've correctly listed all the possible random variable values over here, and they're mutually exclusive, which means if this one happens, this one can't, and so forth and so on, and you've correctly identified the probabilities, well then clearly, absolutely clearly, they have to sum up to 100%, because 100% of the time, as Jenny correctly said, we're going to get from a 1 to a 6. We just don't know exactly where it's going to fall. But here's the question. If theoretically we're supposed to get 1/6 each time, is this evidence that our die are broken in some way? Kate?
Is this the same thing with like flipping a coin and that we're just not using a big enough number? So like when you flip a coin, you might get 4 heads and only 1 tails, but then if you do it a million times.
What should you theoretically do if you're conducting an experiment, like a sample, and you get a result, an average? But that's what those percentages are, right? They're averages. 20% on average, 14% on average. What should the average have with it? Every time. There's no margin of error quoted in those percentages. Now, I've also not shown you how to compute a margin of error on percentages, and that's kind of what 244 is all about. So rather than do that, rather than get into that, let's stick with 243 for right now. What I've done now is I've created a little Excel spreadsheet. What this will do is it will roll dice for us. It's going to roll dice for us. So if you look up here, it uses the rand between command. Now rand between is the same thing. Remember you guys used that rand int command on your TI last week? Right? That rand int command does the same thing in Excel that rand between does. And that generates a random integer between 1 and 6. So right now its first roll was a 3. The pie chart over here will show you the number of rolls of each kind that we got. So 1, right now it's all green because we got our 3. If I hit F9 again, what did I just roll? I just rolled a 2. So now half my rolls are 2, half my rolls are 3. Very small sample. So at this point you can stop and go, okay, my die has 50% chance of rolling 2, 50% chance of rolling 3. And people would laugh at you, as well they should, because it's a ridiculous claim. Let's roll it 6 times. 4, 5, 6. Look what just happened. That's a perfect pie. Now that's extraordinarily unlikely. Watch it 6 more times. 1, 2, 3, 4, 5, 6. Is it a perfect pie anymore? See, now, what I'm getting at here is, we're saying that there's a 1 in 6 chance of a 1, a 1 in 6 chance of a 2. That does not guarantee us that every time we roll 6, we get each number. Did anybody get all 6 numbers in their 10 rolls? Andrew did? Good. Patrick did? You got 2 people? Only 2? Everybody else was missing at least 1 number. Yes, exactly. As a matter of fact, the first 6 rolls that I got up there, when they showed 1, 2, 3, 4, 5, and 6, exactly 1 of each, highly, highly, highly unlikely. It happens about, it's 1 in 120 times. 1 in 100, I'm actually surprised the hell that it happened, but it's going to happen eventually. I've been running this thing for 20 years. It's going to happen eventually. Okay, you ready? Here's 6 more. Now notice what you're seeing. Notice what you're seeing over here in this probability column. Those are the empirical probabilities, not the theoretical ones. Notice how they're not close to 1/6, but they're definitely skewed similarly to how yours are skewed, aren't they?
No, look at your 3 and our 3.
No, I didn't say in the exact same pips. I said they're skewed like yours are skewed. You guys have a 20%, a 21%, there's a 24 and a 29, so there are some that are too high and therefore some that are too low, right Kate?
Yeah.
But Kate, I think, hit upon something special in that she said, we looked at too small a sample. Let me go ahead and roll. How many did you guys have? 217. Let's stop at 217. Let's see what it looks like at 217. There's 217. Compare your percentages to my percentages. What do you notice? They're damn close, but they're still not close to 1/6 on average, are they? But what did you notice about the pie chunks? What do you notice about them? Give me my stapler. Like the guy from Office Space. I need to hold this. This is the one thing I suck at with Excel, is writing VBA code. I need to use a stapler to hold the button down so I can walk away. There we go. Now, what I'm doing is I'm conducting your experiment. We're going to do it a few thousand times. We're going to see what happens. Now, as we're doing this, what are you noticing about that pie chart?
Getting closer to every pie being the same.
It's getting closer to every slice being the same. I know we hit that perfectly in the first 6. Very rare, shouldn't have happened. Does every once in a while, it was an outlier. And that's okay, outliers happen. But what we're seeing now, and look at those percentages. Look at those percentages. Notice how one's still too tall, and one's a little shy, right? We got an 18 and we got a 15. Let's keep an eye on those over time.
That 18's not really changing at all.
What's that?
18's not really changing.
Give it time. Give it time. This is funny. As soon as we got to say give it time, boom, it falls. Because it got ahead early. It got ahead early and then got chewed back down. And that, no, look, there was an 18 popping down there by 5. Look at that. But it can't hold on to it. It's regressing to the mean. It's regressing to the average. This has to happen. This is the beauty of probability over statistics. Statistics is a bunch of people-made rules. Here's how you do an average. Here's how you do a standard deviation. Here's what we're calling an outlier. This is random numbers, friends. There's an 18. The 18 up there. Just watch it. Just watch it. Keep an eye on it. This is random numbers and how they interplay is all it is. This is all it ever will be. And if I let that thing sit there, look, it's trying so damn hard to hold on to that 18, but it just can't do it. Because it can't. Because we know it has to regress to 1/6 each. It can't go to 18% as it goes off to infinity. Let's stop at a nice multiple of 6. What are we at? 3,600, would be 4,200. Let's start with something simple. 4,200. 9. I still feel like doing division. Well, the soundtrack was nice. Go ahead, Harrison.
It's my favorite songs.
I do know that one.
There. Now, right now, how many of each should we be seeing if the 1/6 is operating perfectly? 700. I mean, if we should see 1/6 of each die, of each, 1/6 of the total of each number, we should see 700 of each. We see 721 of these, 697, 663, 707, 719, and 693. Now, some of those seem pretty far away from 700, right? I mean, hell, 663 seems really far away from 700. It would be 36 away. But realize how much you're off by. 36 out of 4,200. That's less than 1% error. That's less than a 1% error, isn't it? When you think about it that way. Now, we were off by a very wide range. We're off by roughly 4%, off 2.5%, about 5%. You see, we're getting at almost on. But we had a very small sample, which means we have to accept a large margin of error. With a larger sample like we're seeing, the margins of error are shrinking down exponentially, basically, more multiplicatively than exponentially, but definitely shrinking as it goes. And that's the difference between a theoretical and an empirical probability. There are precious few things in life that you can assign theoretical probabilities to. But I like them because they allow us to jump into this idea of a probability distribution like this one, and then ask some questions about it. For example, here's a question I have for you. On average, if you roll a single die, on average, what do you get?
We get to 3, 5, 6 at a time.
Well, good, but on average, what do you? On average, I want 1. Well, 4, 2, and a 6 for that matter.
There's a professor or something that did like with heads or tails of the penny.
Heads of the penny. So on average, how many heads should you get?
You should get 50% time, but he did.
So half.
He did it in order to see if kids were cheating or not. He said, like, flip this penny 1,000 times, and then at the end of it, we'll figure out the average. And so he sent it home with kids, and they were like flipping it, and then like you're supposed to be able to get like 6 heads or something like that in a row.
We showed that in the first day of class, didn't
Yeah.
we? Yep. And the ones that didn't have at least 6 in a row, you
Yeah.
faked it. You faked it.
And
Yeah.
this is kind of the same thing with this because it's nature. You can't.
It is, but I'm asking you a more integral question. That's a very, very good point, Harrison. I want a number though. On average, what do you want? 1 through 6? If I want one value though, if you had to summarize that whole thing in one value.
3.5, but you can't land on 3.5.
Well, hang on a second now. Did I ask that? I said on average, what are you going to roll? In 1990, the United States released a census that said on average there are 2.5 children per family in America. Now I remember this, some of you that were, unless you weren't born then, but that's okay. 2.5 children per family. You can't have 2.5 children in a family, but you can average 2.5 children. JC? It's the keys, it's the fair share. It's back to the fair share idea. If there are just as many 1s as 6s, and just as many 2s as 5s, and just as many 3s as 4s, If I take all those pips and spread them to all the rows, how many are each going to have? 3.5. Yeah, now there's two ways you can do this. There's two ways you can do this. Well, actually, there's three ways you can do it. One is reason through it, like JC and Skylar have showed us how to do. That's one way to do it. There's one way to do it. Another way to do it is to use technology. Let me slide this back down again. Use your technology. Well, Excel actually kind of sucks it sucks at distributions. No, let me finish. There are certain things Excel sucks at, and one of them is doing grouped averages. Unfortunately, it's terrible. Did anybody notice when you did your last in class, when I had you do the average number of eggs that my chickens laid, I didn't have you use the frequency distribution that I made you set up? I had you go back to the raw data. It's because Excel doesn't have a good frequency distribution calculation. It's terrible, actually.
You can't think on its own.
It doesn't have a L1, L2, if you will. It also can't do a box plot. I mean, you can, as Andrew tried to discover 17 minutes into a YouTube video, that it takes forever to set one up. So there's just certain things it can't do well, and that's one of them. So I'm going to default back to the TI. So now here we go. Here's method number 2. Method number 2 is use the results that we already got, L1 and L3. Remember those results? Use our results. Stat calc. 1 bar, L1, comma, L3. Remember, I'm using L3 to get the percentages, not the frequencies. What's our average come out as? 3.3. Well, we were saying it was 3.5. Should be 3.5. That's okay. That's because our measurements actually have a margin of error on them, as Kate mentioned. Our sample size is pretty small. But wait a minute, look at our sample size. What did it say our sample size is? Now, this is a little bit misleading. It's actually not a sample size anymore. That's the sum of the percentages. Exactly, Dawn. That's the sum of the percentages. Anybody else notice something that's interesting? There is no sample standard deviation anymore. That's because when you use probability distributions, there is no sample. You're talking about your results as if they were the entire population. Holy crap, this is awesome. This is totally awesome. Because essentially, that means there is no error. But that means also the numbers you put in your column had better be bomb-proof. So, let's come back. Stat, edit. I'm going to change my L2. I'm going to change all those to 1/6. 1/6. 1/6. These are the theoreticals, right? 1/6. 1/6. And 1/6. Change them all to 1/6. Now, if you want, you can graph these. It's going to be kind of boring. What's it going to look like? It's going to be a histogram with a perfect straight line on the top. It's called a uniform distribution. So, Jenny, I'm not worried about your 3s and your 6s and your 1s, because over time they're going to get gobbled up just like that 18% got gobbled up. Okay? Not worried about it at all. It's interesting that it happened in the same way it's interesting that when I ran the Excel sheet, I got 1, 2, 3, 4, 5, and 6 in the first 6 pushes. That's never happened before in class in 20 years, but it's got to happen eventually. It just happened today. Congratulations. Now, if you take a look at this, we change these bad boys to L1 and L2.
How are you in Vegas?
I don't go to Vegas. I know better.
I'll take you sometime if you want.
I don't want to. If I'm going to Vegas, I'm going climbing. Whoops. What the hell? Did I forget to push it again? L2. There we go. There. Somewhat of a boring graph. But that's the theoretical graph. Now run 1 bar stats. L1, L2. And notice your average. I know you can't roll 3.5. I know you can't roll that. But you will average 3.5. And this is why I don't go to Vegas. Because that average, as you'll see on Thursday, is negative in every single Vegas game of chance. And that's how they keep the lights on all night. And that's how they have a city that is nowhere near a body of water with the Bellagio fountains running 24/7. Because people keep giving them money. Because that average will be negative on every game of chance.
I just picture you for some reason being one of those like guys that could count cards.
I could. I don't want to. Vegas disgusts me. For many, many reasons, and you'll see why. You'll see why. You'll see why. I do encourage you guys to read the book Bringing Down the House, which was made into the movie was called 21.
Yeah.
The book's called Bringing Down the House. It's a fantastic read about just that. I could be one of those MIT guys. I don't want to. I've got a 6-year-old for lack of other reasons, but it makes me. It just pisses me off when I watch games like Deal or No Deal with Howie Mandel, which we analyzed in 105. Some of you guys remember that 105. Keep playing. We've come this far. Keep going. Stop thinking like an American and start thinking like a statistician.
Yeah.
You would have known to stop 2 back before you started losing money. You would have known to stop on average. But that's the thing. I can't tolerate that. It just pisses me off too much. I'd rather be here talking with you guys about it, so you understand it better. I'm not saying you guys shouldn't go to Vegas and count cards. Go for it. They'll probably kick you out. It's their prerogative. It's not illegal, but they don't like it very much.
My dad's one of those guys kind of like you too. He thinks about it, but he doesn't like doing it.
I'd rather apply to stuff like my family's, finances and whether or not we should go with an HSA plan. Just so you know, this is the math I used when COC switched our health insurance a few years back. They gave us an option of an HSA, a high deductible health plan. Some of you may have heard of this. If you haven't, I'm sure it's been on the plate in your jobs. It's you pay a higher deductible when you have to use medical services, but your premium per month is lower. That makes sense?
Yeah.
So the idea is, does that make sense for you? And it's impossible.